Let's explore C++ unordered sets, hash-based containers using the standard template library's unordered set. These sets provide a way to store unique elements in a way that is optimized for speed. An unordered set is a container that stores unique elements in no particular order. It's designed for fast retrieval using hash tables. It is part of the C++ Standard Template Library, or STL, and was introduced in C++11. It is generally faster than a standard set for most operations. One thing to keep in mind is that the elements within an unordered set are immutable, meaning they cannot be modified once inserted. Let's look at some basic usage of an unordered set. First, you include the IOStream and unordered set headers. Then, inside the main function, you can create an unordered set of integers called numbers and initialize it with some values, such as 1, 5, 10, 15, and 20. To insert a new element like 25, simply use the insert function. Let us compare the standard unordered set with the standard set. An unordered set is implemented using a hash table, whereas a standard set typically uses a binary search tree, like a red-black tree. The average time complexity for lookup, insert, and delete operations in an unordered set is order 1, making these operations very fast on average. In contrast, the time complexity for the same operations in a standard set is order log n. Elements in an unordered set have no specific ordering, while elements in a standard set are stored in sorted order. Unordered sets generally use more memory due to the hash table implementation, but standard sets are more memory efficient. Performance in an unordered set can degrade with poor hash functions, whereas standard sets support range queries and ordered traversal. So, unordered sets are best for frequent lookups when the order of elements doesn't matter, and standard sets are best when element ordering is important. Here are some common methods for working with unordered set containers. The insert function adds elements to the set. The erase function removes elements from the set. The find function searches for an element. The count function counts the occurrences of an element, which will be 0 or 1 since the elements are unique. The size function returns the number of elements in the set. The empty function checks if the container is empty. The clear function removes all elements from the set. Let's look at a code example. First, include the IOStream and unordered set headers. Then, inside the main function, create an unordered set of integers called nums. You can then insert elements into the set, such as 10, 20, and 30. To find an element, you can use the find function and check if the element exists in the set. If the element is found, print a message to the console. Although elements in an unordered set are stored in no particular order, you can still iterate through all the elements. You can use the begin and end iterators to traverse the set. Keep in mind that the order of elements is not guaranteed between different runs of the program. You can also use range-based for loops introduced in C++11 and later, for a more concise way to iterate through the elements. It is important to note that iterators can be invalidated when the elements they reference are removed from the set. Additionally, all iterators may be invalidated by rehashing, which can occur when the set needs to reorganize its internal structure to maintain performance. In the example code, an unordered set of integers is initialized with some values. Then, two different methods are shown to iterate through the set, first using iterators and then using a range-based for loop, both printing the elements to the console. To use custom types in an unordered set, you need to provide two things. First, a hash function to convert your object to a hash value. Second, an equality comparison function to check if two objects are equal. You can provide these by specializing the standard hash and overloading the operator equals. A good hash function should distribute values uniformly across the hash space to ensure good performance. Poor hash functions can lead to performance degradation due to increased collisions. Let's examine the code example. A struct called point is defined with integer x and y coordinates. An equality operator is overloaded to compare two point objects. A hash function specialization is provided for the point struct within the standard namespace. This hash function computes a hash value based on the x and y coordinates of the point. An unordered set provides access to its underlying hash table structure through the bucket interface. Bucket count returns the number of buckets in the container. Max bucket count returns the maximum number of buckets possible. Bucket size n returns the number of elements in bucket n. Bucket key returns the bucket number where a key is located. Load factor returns the average number of elements per bucket. Max load factor returns the maximum load factor allowed. Rehash n sets the number of buckets to n and rehashes the container. Let's look at the code example. First, an unordered set of integers is initialized with some values. Then, bucket information is retrieved and printed to the console, including the number of buckets and the load factor. Finally, the bucket number for a specific key 5 is found and printed. Unordered sets are particularly useful in several scenarios. They can be used for removing duplicates from a collection of items. Unordered sets provide fast lookups when the order of elements doesn't matter. They are useful for membership testing in a large collection. Unordered sets can be used for implementing caches and lookup tables. They can be used for tracking visited nodes in graph algorithms. You can use them for finding unique elements in datasets. Finally, you can use unordered sets for implementing set operations, like union and intersection. The code demonstrates how to remove duplicates from a vector using an unordered set. The remove duplicates function takes a vector of integers as input, inserts all elements into an unordered set to remove duplicates, and then converts the set back to a vector, which is then returned. Here are some performance tips for working with unordered sets. Reserve space with the reserve function when the size is known. Use in place instead of insert to avoid unnecessary copies. Tune the max load factor for space and time trade-offs. Provide good hash functions for custom types. Consider using unordered multi-set for duplicate elements if needed. Here are some common pitfalls to avoid. Do not modify elements directly, as this can break the hash table. Avoid using mutable objects as keys. Be careful about iterator and validation rules. Watch out for poor hash functions that cause hash collisions. And always remember that elements in an unordered set are unordered. Here are some further resources for learning more about C++ and unordered sets, including C++ reference documentation, standard library tutorials, books like Effective STL, the C++ core guidelines, and websites like cppreference.com. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.